Okay, so we're going to start 16.6. It's on parametric surfaces. And area. We've, in algebra and in your first semester of calculus, curves were the focus. And curves were always y as some function of x. And that works, but it has limitations. Curves like that have to be functions. And there's this whole thing about vertical line tests and all this stuff. And it turns out you can get away from all of the problems with curves if you parametrize them. So parametrizing curves is more flexible than just writing one variable as a function of the other in x, y coordinates. And same thing turns out to be true for surfaces. We've had lots of surfaces where z was a function of x and y, or sometimes we just describe them implicitly where you have a function of x, y, and z equal to some constant. But now we want to do to surfaces what we had done to parametric curves, where we would describe them in terms of two independent parameters. Curves are described with one independent parameter because the curves are one-dimensional. You need two independent parameters to define a two-dimensional object like a surface. So here we go. Okay, so that's a point on my curve. This is going to be r of uv. So r, the vector r is always a position vector in this class, as I think you probably figured out by now. My screen is frozen, so let's see if I can keep that into view. There we go. So there's my surface. R of uv is my position vector. And it's two-dimensional, meaning if you let, what I think I'll do is sort of, let's say we hold v fixed and let u vary. Then you'll describe motion in one direction like this. I'm going to try that again. Okay, so that's where one variable like v is fixed, so allowing u to vary. And then if we do the opposite and make u fixed, then you could get a different curve, maybe like this. Going down the backside. Okay, so this curve on top is with holding v fixed. And I would say with varying u. So that's just a space curve. Okay. And it's one-dimensional because only one variable, one parameter is being allowed to vary. Okay. And of course, the other case is over here, where we are holding u fixed. With varying v. And we know they're independent parameters if those two curves are different curves. They would cross at one point. But they're independent parameters if those are different curves that they don't have to be perpendicular, but they do have to go off in independent directions and only intersect at a point. Okay. And this RVD is a three-dimensional curve, so I should say a three-dimensional surface. So you've got to have three coordinates. There will be an x function of u and v, a y function of u and v, and a z function of u and v. Okay. Just a real quick, let's just use some quick examples. So for spherical coordinates, I want to remind you the transformation rules. Okay, the x is rho sine phi cos theta. Y is rho sine phi sine theta. And z is rho cos phi. And of course, x squared plus y squared plus z squared is rho squared. Okay. On a sphere, rho is a constant. Let's say a sphere of radius a, rho is constant. So the parameterization would have x equal to a sine phi sine theta, y equal to a sine phi cos theta. Oh, I got this backwards. Sorry, guys. X has got to have the cosine, and y has got to have the sine. And z gets an a cos phi. Okay, and that's how you parameterize a sphere. You would need phi to go from 0 to what? Let's see if I can get the chat going here. What would be the limits for phi, guys? Yeah, thanks. Phi has to go from 0 to pi. And theta, as usual, goes 0 to 2 pi. Okay. And that'll sketch out a sphere. Okay, so that's a sphere. And then I want to do an ellipse real quick because ellipses are just like spheres. Okay, so for the ellipse, we could do like x squared over a squared. Sorry, I should say the ellipsoid. X squared over a squared plus y squared over b squared plus z squared over c squared equals 1. Then it's essentially a sphere with 3 different radii. So you could almost just copy everything over for x, y, and z here for the sphere, and just change the radius for each variable. So here's the sphere, but x goes from negative a to a, that's fine. Y goes from negative b to b, so you have to put a b in here for y. And then z goes from negative c to c, so we need to put a c for the z coordinate of each point. And that'll graph out an ellipsoid. Let me do a real quick reminder how that works. Okay, that's a quick kind of ugly sketch. I didn't think that would go well. One more time. Yeah. That's better. Okay, so that's how you graph an ellipse. How about this one? For any function like z equals f of xy, you could do x is u, y is v, and then z would be f of xy, so that would be f of uv. Okay, so that's an easy way to parameterize the surface. You say r of uv is x, which is u, y, which is v, and z, which is f of uv. So there's your vector function. On the other ones, so for the sphere, you'd have r of uv. Actually, we do theta and phi. So it's like phi theta is going to be the x coordinate, a sine phi cos theta, y coordinate, a sine phi sine theta, z coordinate, a cos phi. Just like that. Okay, so that's two independent parameters that vary independently of each other, and those points, and that's an infinite number of points that would trace out a sphere. Similar to the ellipse, which I'll zoom in on here for the ellipse. Obviously, the y coordinate needs to have a b, and the z, oops, y coordinate needs a b, the z coordinate needs a c. And so that's the vector function for an ellipse. Okay. Also on the ellipse, you would have, just as before, you'd have phi going from 0 to pi, and theta going from 0 to 2 pi. Okay. Any questions? Let's do a cylinder. Okay, so a circular cylinder. Okay, so you just do x squared plus y squared equals a squared. And it seems, because it's a cylinder, it sort of makes sense to put it into cylindrical coordinates. So, one thing to remember with a cylinder is that x and y are constrained, but z is not. So you could say x is like r cos theta, and y would be, I shouldn't say r cos theta. Let's do a cos theta because the radius of the cylinder is a. So x would be a cos theta, y would be a sine theta. And then z is unconstrained, so you could just say z is z, okay? So z is just z. So when you write this as a vector function, you'd have an r of theta and z, okay? And x being on the circle would just be a cos theta, and y would be a sine theta, and z would just be z, okay? I don't know that we need to constrain z, but it would make sense to say that theta would be between 0 and 2 pi, but that's not necessarily required. Any questions about the circular cylinder? So most of this is pretty obvious. If you do a cone, let's try that. So a circular cone. So it's been a while, but the cones are x squared plus y squared equals z squared. So we say z squared is x squared plus y squared. And if I stipulate that z is greater than or equal to 0, then I could say that z is just the square root of x squared plus y squared. Okay. Okay, any questions? That's just a function of x and y. And you could say, one parameterization is just that x is x, y is y, and z is the square root of x squared plus y squared. That would work fine. It might be easier to use polar coordinates here as well. So then you would say that x would be r cos theta, and y would be r sine theta. Now we don't want r to be fixed because on a cone, r being the distance from a point to the z-axis will vary on a cone, unlike a cylinder where r is always a, like in the previous example, a being the radius of the circle or cylinder. Okay, but if x is r cos theta and y is r sine theta, then z is the square root of x squared plus y squared, so that's just r. Okay, so this is maybe a cleaner way to parameterize the cone. You would just say r, this is uncomfortable, but we're going to say r of r theta, distinguishing the vector r from the radius r. Yeah, so we could say x is r cos theta, y is r sine theta. Oops. And z would just be r. So that would make a cone. And then again on this, he would stipulate probably that theta would go from 0 to 2 pi. Okay, any questions about that? So there's a handful of surfaces Any questions out there? There's one more that I'm going to do, and then we'll get into the calculus part. Okay. Let's go to a plane. This plane is going to be containing, oops, the point, and I think it works to use r sub 0. It's, remember, points and position vectors are really the same thing. So the point r0, an initial point, and the vectors a and b that are basically a and b have to point in different directions, or it won't work. If they point in the same directions, this plane will not be a plane, it will be a line. Okay, so this is actually super easy. Just very quickly with our coordinate system. Okay, and then I'm just gonna kind of set a plane out here. Just kind of out in space, a plane. Now, this R0 vector is a point in the plane, so this would be our R0 position. Okay. Okay. And then the plane has to contain these two vectors A and B, so I'm going to go ahead and draw an A kind of coming out from that point, A, and then a B just in some other direction, like that. Okay. And basically what you want to do is just recognize that any point in the plane can be found by adding a multiple of A and B to R naught. So basically what we want to say is that R, and this is the parameterization of the plane, R of UV. Okay, we need to set you up in the right position, so we'll start with R0, and then we'll just add multiples of A to multiples of B, and you know that has to be in the plane, and we're just claiming that any point in the plane can be found by picking the right value for U times A plus the right value of V times B, and that would be the equation of that plane. And that's all you need to do. Okay, any questions? I mean, we could do a quick example of this. So just a real quick one here. So give a parameterization. It's really, any surface has an infinite number of parameterizations. Of the plane containing the points. So let's just do 3 points out of thin air. And this plane, see, the nice thing is this can be a vertical plane. It can be horizontal. It can have any orientation at all. That's why we like parameterized surfaces, because they don't have the same constraints on when z is a function of x and y or whatever, because there are all these places where z won't be defined sometimes. And that often can be avoided with a parameterized surface. So here are my points. I'm just going to make up 3 points. 2, 1, 3. Let's say 5, 4, 7, and 6, 1, 2. Let's do 6, 2, 3, bad. Okay. So, so basically what I'm seeing is 3 points. 1, 2, 3, like that. And so let's call them P, Q, and R. Okay, to simplify. Okay, so, and it doesn't matter which is which. This could be, first one could be P, second one could be Q, and the third PR. And what I need is a vector. This first one, PQ, would be like my A vector. And PR would be like a B vector. Okay. And P would be my R naught. Okay, so this is the same thing. Okay, so easy as it gets. So let's do A is going to be R, let's say Q minus P. So you'll do 5 minus 2. So 5 minus 2, and then 4 minus 1, and 7 minus 3. Okay, so that's going to be 3, 3, 4. Any questions there? And then B, I guess is going to be R minus B. So that'll be 6 minus 2, 2 minus 1, and 3 minus 3. Okay, so 4, 1, 0. And you can see neither one of these vectors is a multiple of the other, so they're definitely pointing in different directions. Okay, and then again, this R naught is this P point. It doesn't matter which one you use. So, but R naught is 2, 1, 3. And then the plane R of UV will be R naught plus, I think I had said UA plus VB. Like that. So you could say 2, 1, 3 plus U times A, which is 3, 3, 4. And then plus V times 4, 1, 0. And then probably if you wanted to express this as an X, Y, and Z coordinate, then you need to combine these. So it would be 2 plus 3U plus 4V, comma, 1 plus 3U plus 1b, we'll just say b. And finally, 3 plus 4u. Okay, so that's our plane that contains those 3 points. Okay, any questions about that? So it's still, each point is still defined by 2 independent variables. It's just it's u and v instead of x and y. And you pick the values of those 2 independent variables, and you get an x, y, and a z. So that's a point on a plane. That's pretty straightforward. Any questions? Okay, now it's time to do a little bit of calculus with this. So let's see what we can come up with. Okay, I think I want to go ahead and grab that original graph that we did, and I'm just going to copy this one down. And I think you can just add to the graph up above. So all I really need to do is show what the tangent vectors look like. So, and these will be partial derivative tangent vectors. Oops. Oh, I don't know. This is really bad because I only have one hand. I don't know if it's going to let me work with just one hand on this. So there we go. Okay, and the idea is that if we hold v fixed with a varying u, the tangent vector, and I'll start at this point of tangency and kind of go down like this, that would be r, again, varying u, that would be ru. Okay. And that's actually, I think I drew that too long. I don't like that. So I'm going to shorten it. I don't know what else to do. Okay, so best I can do. There we go. And then I'll do RV. That's holding U fixed and letting V vary. So I'll get a tangent to the other curve. So this one here I'll call RV. Okay. Okay. And then we're doing surface area. So differentials are always, differentials for surface area tend to be found by doing a cross product of 2 non-parallel tangent vectors. So here come my non-parallel tangent vectors making a parallelogram. Yeah, and this is not going to look great, but we do what we must. Okay, I'm going to shade this in so it sort of looks like a tangent plane. Okay, so that differential area is going to be ds. And what I really need to do is make RU and RV differentials. So let's call this RU du here. And RV dv will be parallel to RV. So again, let's just kind of make this RV dv on the other side. Okay. Okay. And so those two differential vectors, that's like a dr is what we used to do with curves. Dr was just r prime times dt. Well, the parameters are du and dv, so we have to say dr, ru, du, and rv dv, which is just like doing r prime times dt, but in two different directions. So those become our differential vectors. And so ds is going to be ru cross rv times du dv. And notice that's a vector. So this the magnitude of ds is is ds the scalar. Okay, so ds without the vector is the magnitude of ru cross rv du dv. Okay. And so the magnitude of ru cross rv du dv. And let me go ahead and just put the whole thing out here. Hang on, I got to erase something. Okay, so this whole thing is just the differential area ds. And that's what's in the diagram here. And that's a capital S. Lowercase s is reserved for arc length. Okay. And so ds with a vector over it, it basically has the magnitude is the area of the differential parallelogram. But the direction is perpendicular to the surface. All right, any questions about just the definitions here? And again, ds, the scalar, is the magnitude of ds, the vector. Okay. So they're very closely related. It's just that sometimes we need ds to be a vector, and sometimes we need it to be a scalar. And you may remember, usually when we dot a vector with a differential vector, we're doing a projection of one vector onto another. And that's done when we compute work. It's also done when we compute flux. So we need differential vectors for flux. That's a surface integral, which is basically what we're working on right now. Okay, but surface area is just a double integral over a surface, call it S, of ds, the scalar. Okay, so that's the definition of surface area. Okay, now if you wanted, you could expound and say, oh, this is an integral where ds is the magnitude of RU cross RV, like that. And then you do your du, whatever order works best for you. And you just do your limits on U and V here. Any questions yet? Okay, so let's try this real quick. So here's a question for you. Find the area of the surface. This is going to be y equals x squared plus z squared. Inside the cylinder. X squared plus z squared equals 16. Which means radius 4. Okay. So this y equals x squared plus z squared, that's a paraboloid opening along the y-axis. So what you want to do is draw one of these kind of a bullet-shaped paraboloids like this, with kind of a circular cross-section here. And then you'd have your y-axis coming out like this. And of course, x over here somehow, and z going up, like that. And I need that maximum radius to be 4 here, because I have to stay inside the cylinder. X squared plus z squared equals 16. That's a radius of 4. So I'm going to draw my maximum radius here like this. That is not a good picture. I'm going to try a little harder on this. Okay, and again, my radius here, so I'm going to pull this off. That's a radius of 4 going up there. Oops. I need to know that y coordinate. And that's easy enough. So if z is 4 and x is 0, you can see right, right here, x is 0, z is 4. So to know the y-coordinate there, you just put 0 squared plus 4 squared, and so your y-coordinate comes out to be 16. So right here, this point has y equal to 16. Like that. Okay, any questions? Chris is asking me to explain the concept of magnitude area. I think do you mean like a vector area? So the magnitude of the vector area is just area. So a vector area is it's equal to just the absolute value of the area. Okay, well, I could just say area. So vector area is area times a unit normal. Okay. So Chris, all we're doing is you're taking some area in a plane like this, or on a surface, but we're doing a flat version of it. So the area could be A here. And then your unit normal could come up perpendicular like that. Okay. Okay. And so A times N, I would just call an area vector. I can't, I hear what you're saying, and I'm not sure you should hang on to the idea of magnitude area. I think I might have said magnitude. I don't know what I said, but let's not get hung up. This is what I've just explained to you is what you need to grab onto, and that is that we start treating area sometimes as a vector, where the vector has direction and magnitude. The direction has to be perpendicular to the surface, and the magnitude is the area. Okay, so that's a vector area, and in terms of magnitude area, I don't know what that means even, so you don't need to worry about it. Okay, and if I said it, then it was a mistake. Okay, so anyway, I'm going to tuck this thing away here. I don't know what I'll do with it. Okay, so what I want to do is I want to parameterize this paraboloid here. It makes sense to use polar coordinates, but it would be in the xz plane. So let's use polar in the xz plane. So I guess you would say x is r cos theta, but z would be r. Yeah, that's fine. Z could be r sine theta. Okay. And then y is x squared plus z squared on this surface. Okay. But that would be just r squared, I think. So your parameterization, I think I'm going to use a capital R, just not to confuse it with the lowercase r. So r of little r theta is my surface parameterization. Oops. Okay. So we've already decided that x has to be r cos theta. Okay. Y has to be r squared. Okay. and z has to be r sine theta. Okay. And then you really need, if you're going to find the surface area, you'll need the limits on these variables. So I'm sure that theta would go 0 to 2 pi. Anybody want to take a guess at the limits on r? Frozen? Nuts. I see your messages. Okay, there we go. So I'll let you guys catch up, but if you think of the limits for R, shout them out. Yeah, 0 to 4. Good. Okay, now to do surface area, we need the differential for surface area. So ds, capital S, that's the surface area differential. Okay, so let's see, we said this would be RU, this would be capital R, RU cross capital RV, and then we would do du dv. That would be sort of the formula, but of course our variables are a little different. So our independent variables here are little r and theta. So we'll do little r for radius and theta, and instead of du dv, we'll do drd theta. Oops. Okay. And now we have some work to do. So we have to do some partial derivatives. Partial of r with respect to little r would be cos theta, 2r, and sine theta. Any questions about that one? And then r with respect to theta. Okay, so now we're going to do derivative of cos, so that'll be negative r sine theta. And with respect to theta, r squared goes to 0. And then r cos theta. Okay. Okay, any questions? Putting some barbs over the vectors that got neglected here. All right, so now we have to do this crazy cross product. So r with respect to r cross r with respect to theta. Okay, any questions? I hope this comes out nicely. Okay, here we go. So for the I component, looks like we're going to have 2 r squared cos theta minus 0. So just 2 r squared cos theta. And then, oops, and then minus the j component. So with that, we're going to go this way, right? So it looks like we're going to have r cosine squared plus r sine squared. Double negative will make a positive. R cos squared theta plus r sine squared theta. Any questions? I'm trying to make space real quick here, so just one second. I think we're all right. Okay, so the K component, to me, I think, is it 2r square sine theta? Right, how's that? Of course, that simplifies. So here goes. This is going to be, is a vector, 2r squared cos theta, comma, is that just negative r in the middle here? And then a 2r squared sine theta, like that. Okay, any questions? We need the magnitude of this. If our magnitudes of these vectors that are cross products, the magnitude becomes an area. So magnitude of r with respect to r cross r with respect to theta is what we're working on now. Okay, so this should be fun. So we're going to have a 4 r to the 4th. I think I'll group these because we're going to have a cosine square theta and a sine square theta. And then there'll be plus an r squared there, right? Did I lose? No, I got the 4s. Yeah, that's cool. Okay, so I guess we could factor that. So you'd have an r squared here. Actually, let's do it. Yeah. So there's an r squared, and then there'll be a 4r squared plus 1. Like that. And the point is to factor that. So when you bring a square root of a square, that's absolute value. So technically, you'd say absolute value of r times the square root of 4r squared plus 1. Okay. Okay, but reminding ourselves that r is between 0 and 4. We don't need the absolute values. And you can say this is equal to just r times the square root of 4r squared plus 1. So that's the cross product that will give area. Technically, this thing is sort of a Jacobian, but I'm not going to go into the details on that. When we do our double integral of ds over our surface, and again, I'm naming the surface S, that's generally what we call it. Okay, so S is the surface's name. And so when we're just saying you add up the differential pieces of S all over S, that's what that says. Okay, and of course the formula says, well, this is a double integral of the magnitude of r, oops, hang on, r, little r with respect to r cross r with respect to theta, and then that'll be a dr d theta. And now I can put limits. So r, I think, was going from 0 to 4, and theta from 0 to 2 pi. And so we got an integral 0 to 2 pi, integral 0 to 4 of r square root of 4r squared plus 1 dr d theta. You could almost split that in, not almost, you could split that into two integrals that are multiplied applied. So first integral, and by the way, I'm going to do a substitution. So kind of obvious here that u is going to be 4r squared plus 1. And what, so du is 8r dr. So we'll have to do 1/8 du is r dr. Okay, so maybe I'll do this in a couple of steps. So first one, I've got the 0 to 2 pi. Then I've got another integral with 1/8. You're just going to have the square root of du, I think. And then we'll have our d theta. U goes from where to where? Let's see. Well, when r is 0, u is 1 here, so that's the lower limit on u. And when r is 4, you're doing 4r squared, so that's 4 times 16, which is 64 plus 1. I think that's 65. That's not nice. Okay. 1 to 65. Okay, so you know, maybe just to show you we can put the 1/8 back here. You really could just make this two integrals 0 to 2 pi d theta because the limits are constant, and then you got the u to the half from 1 to 65. Okay, so I've got the 1/8. I got the 2 pi. I've got a 2/3 u to the 3/2. From 1 to 65, I think. Times 6, 4 goes into 8. 2 times, so is it 1/6? So could I say pi over 6 times 65 to the 3/2 minus just 1 to the 3/2, which is 1. And then I'm not going to do any more with that. I did evaluate it. It comes out to, I didn't actually, never mind. That simplifies. You could write this as pi over 6. I don't want the approximate equal there. You can simplify this as pi over 6, and you could write this as 65 square roots of 65 minus 1. So if you want to do that. Okay, so that's that. So that's a surface integral, but it's just a surface area. It's the simplest kind of a surface integral. And I guess I should do one more thing. How are we doing for time? 7:23. Yeah, let's do one more thing. Everybody okay out there? Okay, so I wanted to do a real quick development of what happens when z is a function of x and y. So just real quick, this is theoretical. So if z is some f of xy, then let's just say the parameterization is, again, we've said already x will just be x, y can just be y, and z is f of xy. So my position vector is r as a function of x and y. So x is x, y is y, but z is f of xy. Okay, so that's one way of doing it. I don't even need to use a u or a v or anything like that. Okay, any questions? All right, now I want to go ahead and do ds as a vector and a scalar. So ds, the vector, is going to be rx cross ry. So you just do both partial derivatives and do the cross product, and then I'll have a dy dx like that. So you can call that dA if you like. Now I was referring to this thing as sort of a Jacobian. It is. But I'll just let that ride for now. So Rx cross Ry. Let's go ahead and do the Rx here. Rx would be 1, 0, fx. Okay. Just doing this function. And then Ry would be the derivative of x is 0, of y is 1, and then you have an fy. Okay. And then maybe over the side we can squeeze in a cross product here. So Rx cross Ry is what I want for the differential. Okay, so here goes. I'm going to have a 1, 0, fx, 0, 1, fy, and then the ijk's. Okay. And the I gets 0 times fy minus 1 times fx. So I think it's just negative fx. I gotta think about that. I think it's okay. Then minus j gets the 1 times fy minus 0 fx. So this just gets an fy. Okay. And then plus k gets the 1 times 1 minus 0 times 0. So it's just k times 1. So this vector differential is negative fx, negative fy, and then just 1 for the z coordinate. So ds is equal to negative fx, negative fy, 1. Dy dx we'll just call dA. I sort of want to do a little bit of a picture here. I want that parallelogram, but I also want that unit normal. So I'm just going to have to do that on the next page, I guess. So I've got my surface here like that. And I've got my two tangent vectors kind of going like this and like this. So that might be fx here. Sorry, no. That's rx, my bad. So that's like rx here. And down here is ry. And I probably want to change the order of those, so forgive me while I do ry pointing to the. So I'm trying to think about my right-hand rule. Yeah, so I'll do rx. It doesn't matter. Rx to the right, ry out. And then I'm going to have ds going up this way. Okay. And I've got it pointing up. It's an upward normal because the z component is positive. So this is upward. Coming up from the surface, but it's not pointing straight up. It's normal to the surface. So I'm actually going to tweak that a little bit. so that it doesn't look like it's coming straight up. So I'm gonna have to go this way kind of. Okay. So that's an upward normal. Okay. And that's going to be important. Sometimes we want these ds differentials to point down. Okay, so just to make a comment here, if we want a downward normal, we can just change the sign of this. So we would, for that case, we would do ds would have just fx, fy, and a -1 dA. So that's a downward normal. Okay. Either way, just remember ds, which is the surface area differential. This is the magnitude of ds, the vector. Okay, and of course this would just be the square root of fx squared plus fy squared plus 1 dA. Okay, and then the only purpose of pointing that out is to sort of take you back. So now I'm going to fly back to double integrals. Okay, so here's 15.5 when we were covering surface area the first time as an application of the double integral. You know, we did a completely different development, but there's our ds again right here. So this is the same, okay, as what we just developed using a parametric surface development, but it's the same computation in the end. All right, so let's go ahead and we're long overdue for our break, so let's take our 10-minute break. And I'll see you guys in a little bit. And just wanted to go back. I was using the wrong syntax on GeoGebra. So I just, maybe I thought I'd show you, for instance, we had done a cylinder at one point. Let's see if I can find that. Okay, so the cylinder was this one. A cos theta, A sine theta, and then Z, where A is just the radius of the cylinder and Z can range however it wants. I think I'll use a U for theta, and I don't mind letting Z be Z. So just real quickly, I wanted to jump into GeoGebra, and you can see I was playing around with this already, but just to walk you through it, I would just do GeoGebra 3D again. And the funny thing that I misunderstood is that you don't put the vector in brackets. You just list it. You just list the x, y, and z coordinates separated by commas. So the command is just surface. So you just type surface like that, and then in parentheses, you just start by giving first the x coordinate, and I think we said x is like r cos theta. I'll do a cylinder whose radius is 2, so we would do 2, and then the cos of an angle, and you can use whatever letter you want. I think I said I would use u for theta. And then, so that's the x coordinate, and then a comma, and then the y coordinate was 2 sine u. Oops. So 2 sine of u, and now another comma, and then the third coordinate was just z, like that. So you've got the x, the y, both of those, x and y are on circles of radius 2. You should recognize that as the parameterization of a circle. But then we're letting z just vary independently. But then you have to give ranges for the u, which is my theta. So I'm going to say u should range from 0 to 2 pi. So in GeoGebra, see, I wrote that. I just wrote comma u, comma 0, comma 2 pi. Those are the limits for u. And then v, I'm going to have 0. I'm just going to have my z, I should say, is going to go from 0 to 4. So I'm going to say z comma 0 comma 4, and so that's just handled natively in GeoGebra. You don't have to do anything special to do a parameterization like this, and you can do multiple parameterizations in the same graph. Okay. So is there any question about that? I feel like I want to get redeemed on my sphere, so I don't know, I couldn't edit these well. But so I think I'm just going to refresh the page and dump my last graph. And again, type the surface command. And in parentheses, the x coordinate on a sphere is radius times sine phi cos theta. So I'm going to do a radius 6, and then I'll do sine. I think 6 is too big. I think I'm looking at the coordinate system. I think I'll do a radius of 4. So 4. It's sine phi cos theta. So sine, I was using v for phi because it rhymes. And then cos of u for theta. Okay, so that's my x coordinate. Then a comma, the y coordinate would be 4 sine phi sine theta. So sine v and sine theta, which is my u. Okay, and then the z coordinate was cos phi, so that'll be cos of v. And now you don't make this into a vector. All I did was list each individual component for the sphere. And then it needs limits for phi and theta. Again, phi is my v. So I need v to go from 0 to pi, and I separate all those with commas. And then theta is my u, so I needed u to go from 0 to 2 pi. 0, 2 pi. And if I, hey, that's beautiful. It's a pancake. And it's done that because my scaling is a little off, okay? And I'm not sure initially how to change the scaling on an iPad. Maybe there's a problem. Oh, I didn't do 4, I see. So I need to put a 4 in front of the z coordinate, so I'm going to go out and change that. Should be 4 cos v, and that'll scale it up better. And let me see if I hit enter. That's better. So that's a lovely sphere in GeoGebra. And I say that works pretty good. You just got to type surface, list the x, y, z coordinates, and give lower limits and upper limits. So let's put that in to the notes in case you want to do one of these. Okay, so real quickly, I'm going to pop over. How about if I squeeze it in? I'm going to put it right here. So GeoGebra 3D. Okay, let's say your function is r of uv. And let's have that be, as I said before, x of uv, y of uv, z of uv, like that. There would be limits on u. So let's say a to b for u, and c to d for v. Okay, and then in GeoGebra, you would just type. Let's just write. How about if I say the syntax? You would just type surface, and it doesn't have to be capital S. So you would say surface. You list your x of uv, your y of uv, your z of uv, and then you give the limits on u. You would just say u, comma a, comma b, and then v, comma c, comma d, and that'll graph your surface. And it works better on a computer that has a regular keyboard and a mouse, I think, than a tablet. But you can be done. I'm doing it on a tablet right now. Okay, any questions about the GeoGebra graph? Just looking at my chat, if you have any questions, let me know. All right, let's get back. I think we should probably do our notes for then at least start 16.7. And that's on surface integrals. So just as a reminder, if S is a surface parameterized by R of uv with these vector components x of uv, y of uv, and z of uv. Okay. And I can give limits on u and v if I like. So I can say a less than or equal to u less than or equal to b, C less than or equal to V less than or equal to B. Oops. Like that. Then just to remind you, ds here is just RU cross RV, du dv. This is a vector differential for surface area. So it's a vector surface area differential. And that means that it's normal to the surface. Cross product is always perpendicular to both vectors, and those are tangent vectors. Okay. And then ds, the scalar, is the magnitude of RU cross RV. And that gets a du dv also. And so this is just the surface area differential. Okay, we need those both of those in surface integrals. And then don't forget, we also did if S is, oh, I didn't need to say if twice. Okay, so if S is parametrized more as a Z is a function of X and Y, and then we can have limits on X and Y. And these don't have to, this doesn't have to be a rectangular domain for X and Y. But just for the heck of it, I've done that. Then don't forget that we've come up with a couple of different things in this context. The ds, the vector, was, I think it was negative fx, negative fy, 1 dA. That was the upward normal. Okay. And ds could equivalently be fx, fy, and negative 1. Because the z component's negative, that's pointing downward. So that's the downward normal. Okay. And it just depends on the context of what you're doing. Sometimes you'll want an upward normal, sometimes you'll want a downward normal. Okay. And then we're thinking of these in terms of flux. And the normal tends to point in the same direction as fluid flow, or just whatever the direction of your field is, but not always. Okay, so you'll see this as we go. And then don't forget ds, the scalar, is the magnitude of ds. And this is a case, this is truth for every case. It's the magnitude of ds, the vector. And so we've said this is the square root of fx squared plus fy squared plus 1. And of course, dA. Okay, so these are just sort of formulas that are good to have handy as you do surface integrals. So under surface integrals, there's a vector integral and a scalar integral. We'll do the scalar surface integral first. Okay, so you just do an integral. Actually, these are double integrals over a surface. And you're just integrating any old function, scalar valued, of 3 variables, and multiplying by surface area. That's it. Some function times the surface area. Okay. Now normally F could represent mass density. So this would be the mass of a surface, something that has very little thickness, basically. Okay, so this can be used to compute moments. I'll say any moments. It could be first moment, second moment. There are other moments as well. We'll just say moments. Moments of inertia, don't forget, and center of mass. For a shell, basically. A shell-like surface. How about that? Okay. If it has mass, then it has a center of mass, and it has moments, and it has a moment of inertia. If you're going to spin it, think of a hollow sphere. If you want to know the moment of inertia of a hollow sphere, like a globe that you spin on an axis, the moment of inertia would be a surface integral because it's just a shell. The sphere is hollow. So you have to do with this. It's a double integral, not a triple integral. Okay. Any questions? Let me see what I've got here for examples. I guess we should just lay out what this represents. So if S is R of UV as defined above, this is just all about substitutions. So you would do double integral over S of f of xyz ds. So you do a double integral. This would be f of x of uv, y of uv, z of uv, like that. And then you'd have to multiply by the magnitude of RU cross RV, like that. Let me get some space, and then I'm going to put a du dv outside of all that. Maybe I'll do dv du, somehow that sounds better to me. And then I put limits on v as being, I think we had, well, u went from a to b and v from c to d. So it's just a double integral, but all the points you're integrating over are on some surface. Okay, and you're just adding up the function everywhere on the surface and multiplying by surface area. Okay, again, you would do that if the function you were evaluating was density, and if the density is mass per unit of surface area, and you multiply that by surface area, then you just get mass. Okay, so so you get that. Let's see if we've got an example here. Well, I'm going to set one up, and maybe not evaluate. Let's get it set up completely though. Okay, so little example here. Okay, so example, S equals a sphere of radius 3, centered at the origin. And I said sphere. I should have said spherical shell. Forgive me. Please forgive me. Spherical shell of radius 3, centered at the origin, with mass density at XYZ of, let's say, I think we do delta for density here, so delta of X, Y, Z, and I'll just do Z squared. Keep it simple. Okay. Now, the mass would be a double integral over the surface of the density. And this is density per unit area times area, but this is surface area, ds. Okay. Okay, any questions? So this is actually a lot more work than it looks. Easy enough to put the delta is z squared. So we have this double integral over the surface of just z squared ds. That looks so nice. Okay, but what the heck is ds on a sphere? Well, the funny thing is, it's sort of obvious. But I'm not going to do the obvious thing. We're just going to go ahead and bite the bullet and go the whole way. It's going to be horrible. So let's do the sphere. So we've talked about, this is sphere of radius 3. You know what, you guys, also I'm going to do another change. Let's do a sphere of radius A so we can have this generalized. So up here, I've changed the radius to A. Okay. And so that this will work for any sphere for you. You can just substitute whatever, you know, if they want to do a radius 3 at some point, you can just change A to 3. Okay, so the sphere would be like an R of theta. I think I did phi theta before. And what we said was that the x coordinate is A sine phi cos theta. Y coordinate is A sine phi sine theta. And the z coordinate is A cos phi. Okay, like that. And we remember that phi ranges from 0 to pi, and theta from 0 to 2 pi. Oops. Okay, so that's sort of old news there. But I don't know what ds is. It's a surface area differential. I want to do ds to the vector first, and then we'll take its magnitude. Okay, so ds, the vector, not needed here, but it's ru cross rv du dv. Okay, and maybe while we're at it, we'll say ds, the scalar, is the magnitude of ds, the vector. Okay, so that's the magnitude of ru cross rv. Okay. Du dv. And it's 8:11. Okay, here we go. Let's do ru cross rv. First of all, ru. Our independent variables are phi and theta. So let's change these to phi and theta. Like that. Okay, and now we're going to do our phi. We've done something like this before, you may remember, in the context of Jacobians. It's been a while. Anyway, here goes our phi. So I'm going to do A cos phi cos theta, A cos phi sine theta. And then again, with respect to phi, you'll have a negative A sine phi. Okay. Okay. And now r theta. Forget it. Here we go. So r theta is going to have a negative A sine phi sine theta. A sine phi cos theta. And then the derivative of the z coordinate with respect to theta would be 0. Like that. Okay. We got to do this cross product. Not loving the idea, but here we go. R, and not the magnitude yet. We'll just do the cross product. R phi cross R theta. Okay, so here goes. Well, I feel like just sort of putting these in. So here are the coordinates for R phi. Okay, and then R theta. I'll let you guys catch up to that. All right, so these are the I's, J's, and K's. That. Any questions? Yeah, I mean, this totally reminds me of Jacobians. A little different. Okay, here we go. So for the I component, I'm going to do this way. So it looks like I'm just going to have an A squared sine squared phi cos theta. I'm going to double check that. Nothing, A squared sine squared phi cos theta. Yeah, so that's I. Now, the J looks like it may be similarly nice, minus J. Okay, so then I get a 0 and minus a double minus a negative. Minus a double negative, so it would be a minus. A squared sine squared phi sine theta. Like that. I think the K part is the part that needs a little more work. Okay, so watch out now. Here comes the k component. We're multiplying diagonally here. So we're going to have an a square. There's going to be a sine phi, cos phi, cos square theta. Okay. And now the compression begins. See if I can pull this off. Not that much. Not bad. Kind of like that. Almost there. So the next component is I'm doing the upward multiplication, so that's going to be minus a negative, so this will become a positive. And you're going to have a squared sine phi cos phi sine square theta. Look at that. Okay, so I don't know if you can tell, but there's a sine square plus cosine square and all of that. Let's do this in a couple of steps here. So the first component's got this a squared sine square phi cos theta. The j component's got the a square sine square phi sine theta. Okay. The k component gets an a square sine phi cos phi. And then a cosine square plus sine square of theta. Okay. Now, I want to write this as, I want to factor out an A and a sine phi, I think. Okay, and what you get is a sine phi cos theta. And then there's an a sine phi sine theta. And then if you factor out a squared, no, if you factor out a sine phi, you're going to have an a cos phi left inside. And the rest of the z coordinate is just 1. Okay. Now, if you look back, that's this. This thing right here is that thing. So, that's a position vector on the sphere. I might just back this up and say this right here is our r of phi comma theta. So this is a r sine phi. Is what that is. So ds, the vector ds, is r phi cross r theta, the phi d theta. Okay. But we just did the math, and that's a r sine phi d phi d theta. Oops, yeah. And r, that's the position vector. R of phi comma theta. Now that's handy to remember because we don't forget that ds, the scalar, is just the magnitude of ds, the vector. Okay. So this is just going to be the magnitude of a r sine phi. And I don't really want the d phi, and these are positive, so I don't need them inside. Okay, like that. Okay. And a is the radius, it's positive. Phi, you may remember phi is between 0 and pi, so sine phi, that's quadrant 1 and quadrant 2. So sine phi is greater than or equal to 0, with phi between 0 and pi. Okay. A is positive also. So the point is that I can rewrite ds as a magnitude of r times sine phi times d phi d theta. And what's the magnitude of r on a sphere? Anybody want to take a stab at that? Now remember, this is a surface integral. You live on the surface. You're not inside the sphere, you're on the sphere. And what's the radius of the sphere? Well, that would be the magnitude of r. So what's the magnitude of r? Anybody? Not getting anything? Again, the magnitude of r is the distance from the origin to a point on the sphere. That is by definition the radius of the sphere. So the magnitude of r is a, and therefore ds is a square sine phi d phi d theta. Remember, the radius of the sphere, the equation of the sphere is rho equals a on the sphere. So you're living on the sphere. Remember, you want to contrast this to dv is rho square sine phi d rho d phi d theta. So when you're inside of a sphere, or it doesn't even matter, when you're in spherical coordinates, d square has a Jacobian, that's rho square sine phi. But if you're on the surface of the sphere, then ds, because it's a shell, not a volume, ds is a square sine phi because rho is a on the sphere. Okay, so you're not allowing motion into the sphere, but phi and theta can vary, and ds is a square sine phi. Okay, any questions about that? Okay. So I have to go all the way back and evaluate my surface integral. So way back. Here it is. So I'm going to just copy this guy down. Okay. And come down here and just start evaluating stuff here. Okay, so double integral. Don't forget, on the sphere, z is a cos phi on the sphere. So when you do this double integral, z squared just becomes a cos phi. That's z squared. Okay. And then ds gets an a square sine phi. And now we can say d phi and d theta like that. Okay. And then phi, of course, from 0 to pi, and theta from 0 to 2 pi. Any questions about that? I don't know. We can try and evaluate this real quick. It doesn't look too bad. So it looks like we're going to have an a to the fourth coming out. And here comes the integral. This is all in phi. So I could do one integral from 0 to 2 pi just on d theta, like that. And then there's another integral here from 0 to pi of just cos square phi times sine phi d phi, like that. And then, of course, u will be cos phi. Okay, and so du will be negative sine phi d phi. Like that. And we can expect our limits to flip when we do that, but let's keep going. We got an a to the fourth, okay, times the integral of d theta from 0 to 2 pi, that'll just be 2 pi, okay, times the integral, I'm going to have a minus sign, I'll put it inside right now. So I'm going to have a cosine squared, which is u squared, and then a negative du, I guess. Remember, whenever the differential comes out negative, you can count on your limits being flipped around wrong. So this is negative, and so we see that when phi is 0, the cosine of phi is u, so cosine of 0 is 1. And when phi is pi, cosine is negative 1, right? So because those limits are backward, we have a negative differential that corrects that. Okay, so it kind of help you understand what differentials do. It keeps track of these transformations. This is a transformation that's inverting our region, so the integral comes out negative. Okay, so this is 2 pi a to the fourth. I guess we can put a 1/3 u to the third from -1 to 1. I just kind of change the limits and make this whole thing positive. So it's 2 pi a to the fourth times 1/3, and you'll have a 1 to the 1 minus -1 here. So I guess we can finish this and say it's 2. Well, how about 4 pi a to the fourth over 3. Just like that. So that would be the mass of this hollow shell. So that's just sort of an example of a surface integral where you're adding up just on a surface. So that's kind of interesting. Let's do another example here, where we go into the flux integrals. Okay, so just real quickly, we've already introduced scalar surface integrals. That looked like this. Double integral over a surface of some scalar valued function, like a mass density. Like I said, it could be a probability density function if you're trying to find the probability of a particle being on a surface, times surface area. Okay. So, and as we said, ds is that's the surface area differential. But then there's a vector surface integral. And this is the surface integral of a vector field over a surface. So the vector field would be like F over the surface S. Okay, so the integral looks really similar to double integral over the surface, but here we put a vector field in which has vector output. So big F of x, y, z, and then we're dotting that with ds, the surface differential vector. Okay, and then just maybe a quick kind of a reminder here. Probably there's a lot worth talking about on this. So let's go ahead and draw a little surface. And we'll put our, this is our surface S, okay? And just a real quick statement of what ds is again. Ds is just a unit normal. The unit normal gives direction to this surface area. Okay, so unit normal. And then this is the surface area differential. Okay. So if we want to plop one of those on here, it's going to kind of go like that. So that would be ds. Actually, I'm going to move over to the side here. And while I'm thinking about it, let's just do the unit normal here. Okay. And then we'll have ds be the area. So you may remember that ds is the magnitude of a cross product. So we're going to have like an ru du going in one direction. So I'll have this one be ru du, and the other one being rv dv. Okay. And then maybe we'll just make our little parallelogram that represents ds.
like that. And then ds is the area of this. That's too small. Like that. Okay, and then there's a field that's flowing across the surface. So we think of this as it could be like a magnetic field or an electric field. So let's go ahead and do our field, and let me make it a little thicker. So here's a field vector that's touching this surface at a point like that. Okay, and so the field is when you dot it with this unit normal, you're getting the normal component of the field. So let me go ahead and see if I can do a projection here. So I'm gonna tweak this picture a couple of times as I go through it. But I want to do the normal component of my field. So I'm trying to get a good perpendicular there. So just your patience as I pound this out. Okay, so that, actually I'm going to do one more cut on this. That's good. Okay, so when we do f dot in, we're just measuring how long the normal component is. So let me see if I can add some more here to make that clear. Okay, so from here to here. Oops. Okay, so what all I mean to say is that this distance right here, that's f dot in. Okay, so, and maybe just to put it down in words here, we've done projections many times, so I don't want to go over projections again, but f dot n is the component of F that's normal to S. Okay, so that's just the meaning of that part. Okay. And when you do F dot N ds, now you're multiplying by surface area. So F dot N ds, capital S there, is the normal component of F times the differential surface area. Oops, sorry about that. Let's see here, surface area. Okay, and this is called the flux differential. Okay, so if F is a velocity field of some fluid, so let's put this down. If F, and it doesn't usually, by the way, but this sort of gives us a feeling of what we're computing when we put it in the context of a fluid flow. So it's rarely a fluid; it's usually a field. But regardless, if F represents the velocity field of a fluid, let's say flowing through a porous surface. Let's say the porous, is that how you spell it? Surface. It could be like a filter. Oops. S, then flux is a total fluid, and I'll show you this later. It's a total fluid flowing across S per unit time. I should say flowing through S, that's probably a better word. Flowing through the filter, okay, per unit time. Okay, so you've got this flux differential, F dot N ds, so total flux of F through S, you would just sum up on this flux differential. So you do a double integral across the surface of F dot the unit normal ds, like that. But the unit normal times ds is just the ds vector differential. So like this, F dot ds, this way. Okay. And so just as a reminder, the F field has to, is really a function of x, y, and z, which has component functions p, q, and r. Okay, so that is the field. So Harry, and then just a reminder that ds is ru cross rv du dv, or dv du in either order, where S is parametrized by R of UV. Okay. Not horrible. And this is not, I mean, what's the hardest thing here? It's not a new skill. These are just definitions. You know how to do double integrals. So the question is, if I ask you to compute the flux of a field through a surface, can you set the integral up? It's not, can you evaluate the integral? I mean, it is a little, but I mean, setting this up, this is a challenge. Okay. Okay, so we're going to do a quick example. Okay, so here we go. Let's say our field has components x, y. Sorry, my bad. It's y, z, zx, xy, like that. The surface S has z equals x sine y. Okay, where x goes 0 to 2. And y goes from 0 to pi. Okay. So there was another scenario that I'm going to copy and paste down from our prior discussion. So let's see here. We also have this expression here that I'm going to copy back to our notes down below, because ds can take a different form depending on how it's defined. So let's just put this down below as part of our notes. You can just refer back up to it in your notes. Okay, so I'm just going to put this in and kind of make it small. Oops. Okay, so so this is our prior ds when z is a function of x and y. Okay, and of course you could have x as a function of y and z, etc. And you'd have to kind of alter the discussion here. Now I need to know whether this normal is upward or downward. I'm looking at my notes and it says we want to do an upward normal on this surface. Okay, which means we need to pick the ds from our prior discussion that has the upward normal. So here we go, ds is going to have negative fx, negative fy, 1 dA, like that. So the x sine y is our f of xy. Here. So we can go ahead and just start evaluating this. Negative fx, well, with respect to x would be negative sine y. Okay. And then negative fy, that would be negative x cos y. And then the one that has a positive, it always got this positive z component. And we'll put our dA in here. Okay. Any questions? Now we're computing flux. Remember, flux is a double integral of f dot ds. Let's go ahead and do f dot ds real quick. We've got everything here. So the f again from above. We'll put down here, and then ds. But there, that's a dot product. Could be ugly. Okay, so here goes. We're going to have a negative yz sine y. And then a negative x squared z cos y. And then just plus xy. That's horrible. And then dA. Only thing that's a little disturbing in all of this is that there's a z in here. So you can't have a double integral. Remember, the dA is going to be dy dx. Okay? And you can't have a z in there. So this is where you're going to have to remind yourself that z is x sine y. And do that substitution. So all of these integrals are all about just loads of substitutions. As you can see, we're doing one now. So I'm going to do a negative y, and z is an x sine y. So this is a negative x y sine y times another sine y. So it's going to be a sine square y. Now we've got an x squared z. So that's going to be an x to the third sine y cos y. Okay, and then plus the xy. And now dA. So I'm going to double check this to make sure it's not wrong. Okay. And so then the flux, I just got this from the book. So the flux, the total flux would be the double integral of f dot ds. Okay. It's easy enough to put limits on this. X goes from, well, first of all, I got this over the surface, so now we'll put this into a double integral with this big mess in here. Okay, and I don't think it really matters what order you do this in. I did y first, and then x. So y goes from 0 to pi, I think. And x from 0 to 2. So that's how you set up one of those monstrosities. I am just going to give the answer to that one. I'm looking at all my work on this. This comes out as pi squared over 2. And we've evaluated a lot of double integrals. This one's already set up. Point is setting it up. Okay. Any questions? Let me know. And I'll be happy to talk to you during my office hours or something like that. Okay, I'd like to do Gauss's law real quick. Which is for flux of an inverse square. I'm putting this in a sort of a general context. Okay, so this is for flux of an inverse square field. Across a closed surface. S, and we'll go ahead and S containing the origin. We'll assume S is a sphere to simplify this, and then later on we'll talk about how it doesn't matter what the surface is. Okay, so we'll assume that S is a sphere of any radius. Let's say it's A. Okay? So, there's a convention, and that would be whenever we work with closed surfaces, oops. The surface normal should point outward. So that's the ds vector, which is little n times ds. So you can think of that as the unit normal pointing outward, or ds, the vector pointing outward. They'll point in the same direction, and that needs to point out of the surface and not into the surface. Okay, so let's say should point outward. Now, if you point it inward, what happens is your dot product will come out with the opposite sign. It'll be negative when it should be positive, or vice versa. So it's not a big deal. You just change the sign of the answer, and nobody's going to make a huge fuss about this. But it's a convention, and you should try and remember it. Okay, so we've talked about inverse square fields. And that would be like in 16.1, I think we did the first one. So they look like this. Big F of x, y, z. The simplest version we said was some multiple of the position vector over the magnitude of the position vector to the third power. Okay. And how that came about, I think I'll leave you to go back and look it up. But you've got this k. The r, again, position vector is just x, y, z, like that. And the magnitude of that is the square root of x squared plus y squared plus z squared, but then you have to raise that to the third power. So you're going to do an x squared plus y squared plus z squared. Again, the square root of that to the third makes it a 3 halves exponent. Okay. And then the flux is going to be surprisingly easy to do because of some of the prior work that we've done to set up the surface of differential for a sphere. So here goes the flux. So doing a double integral over surface S, and when we put a circle around this, this implies S is a closed surface. That's standard math notation. Okay. And the surface integral for flux is f dot ds, like that. Okay, so we can go ahead and just put in our field. So actually, I'm going to put limits on this right away, I think. So I'll just do a double integral here. Now the field, I think I'd like to use the original form. This is k times r, the unit, the position vector, over the magnitude of the position vector to the third power, like that. Now ds, the vector differential for surface area, let's go back and find it because we already did this for a sphere. I think this is it here. So we want the vector differential, so that'll be this one right here that I'm wiggling about. Okay, so let me copy that and we'll paste it down below. Okay, so you get an r dot r in there, so this is kind of an interesting outcome. We can go ahead and say, look, we're integrating over the surface of a sphere. Remember, there's no rho does not vary freely, so there's no d rho in this. You're stuck on the surface of the sphere. The only thing that really can vary is sort of your latitude and your longitude as you move on the sphere. But no, you're not going into the sphere, just over it. So you see phi and theta varying. Now, phi, of course, will have to go from 0 to pi, and for theta, you need to go from 0 to 2 pi as you move around the sphere. That's just the standard range for phi and theta as you move along a sphere in spherical coordinates. So let's do a little work on this here. So I see that r dot r. I kind of want to bring the a out and maybe the k. So let's do a, k, and then inside we've got this r dot r, and down below you've got a magnitude of r to the third, and then sine phi we're not going to get rid of, that has to stay, and then a d phi and a d theta. Okay, put the limits in, like that. Note r dot r, maybe over to the side, you may remember r dot r, I hope you remember, is the magnitude of r squared. Okay, so that's looking better. So we've got the magnitude of r squared over the magnitude of r to the third, and then the sine phi, d phi d theta. Okay, and of course we just get a 1 over the magnitude of r on that. It's interesting. Now, this is a sphere. So, motion is constrained to the surface of the sphere, which means that r does not vary randomly. Okay, so let's put this note in here. Motion is constrained. It is a surface integral. To the surface. So that means the magnitude of r has to be the radius of the sphere, which is a. Can you handle that? So that means I could get rid of that magnitude of r there. Now it's not your position vector that's constant. It's the magnitude of it that's constant. So you got this a k integral 0 to 2 pi, integral 0 to pi. This is just 1 over a sine phi d phi d theta. So the a cancels. Okay. Now, I like to think of clever things, if I can. Okay, so let's go ahead and write this down. This is a k, can't get around it. Integral of 0 to 2 pi. Integral of 0 to pi, and I just get sine phi d phi d theta. Okay, that's fine. And you could do that. You could do the painful process. But I like to avoid integrating when I can, and I want to remind you just here, we're going to do a little trick here. So recall. Oops. That ds, and again, a lot of you guys, I wouldn't expect you all to recognize what I'm about to do. I've just been doing this so long that I know some of the tricks. So I know that ds, I think, if you go back to the notes, actually, let's just see it here. Okay, so did I ever say? Oh, here we go. ds, the scalar, is a square sine phi d phi d theta. Okay, so I'm just looking at this thing right here. That's for a sphere, only for a sphere. That's the differential for surface area. Now that's the scalar differential, not the vector differential. A square sine phi. So let's try this. So ds, is a square sine phi d phi d theta. Okay? And so what I want to do is I want to make this look like a ds. So what I'm going to do is I'm going to do a k over a squared, like that. And then this is integral 0 to 2 pi, integral 0 to pi. And then you're going to have an a square sine phi d phi d theta. Okay, so this is just ds. It just looks so much like ds that I wanted to make it ds. Because in the end, you got this k over a squared, a double integral. You're still integrating over the sphere, just ds is what you're doing. Okay. You can even put this circle on here again. And this should just be the area of S. So you've got this k over a squared times the area of S. Okay. And so you have to know the area, the formula for the surface area of a sphere. Okay. So I would say, okay, that's pi times, what is it? 4 pi radius squared. Okay, so is k over a squared times 4 pi a squared. So that's the area of a sphere, surface area of a sphere. Okay, so in the end, you just get 4 pi k. Okay, and notice this is independent of the radius of the sphere. And so it's sort of interesting because, if you think about it, we think about flux as sort of fluid flow across some surface or through a surface. And so we've got this, some source of fluid on the inside of the sphere, spherical shell, that's flowing out across the shell. And all we're really saying here is it doesn't really matter how big the shell is, and in the end it doesn't really matter what shape the shell is. If you think about the flux, which is the total fluid flow, it's all going to flow across this sphere. It doesn't matter how big the sphere is, you're still going to have the same amount of fluid flowing through it. So this is basically a statement of Gauss's, what's called Gauss's law, that flux for the inverse squared field across this surface is going to be independent of the surface itself, as long as it's a closed surface and as long as it contains the origin, which is the source of the fluid flow. Okay? So that's Gauss's law. And it turns out to be independent of the surface altogether. As long as it's closed. There's just a lot of things in this class that sort of remind me of each other. Like we talked about in a conservative field. Well, inverse square fields are conservative. We talked about how in a conservative field that if you compute work from one point to another point that the field does to move something along a curve, it turns out it's independent of the curve. The only thing that matters is the change in potential energy at the endpoints. So when you do when you do work through a field that's conservative, it's independent of path, we say. And here we're saying that the flux is independent of the surface, and you'll see more of that